And here we go. All right, and we're back for the second to last chapter, chapter 19, Object Pool of Game Programming Patterns. Let's just hop right into it. Intent. Improve performance and memory use by reusing objects from a fixed pool instead of allocating and freeing them individually. Motivation. We're working on the visual effects for our game. When the hero casts a spell, we want a shimmer of sparkles to burst across the screen. This calls for a particle system, an engine that spawns little sparkly graphics and animates them until they wink out of existence. Since a single wave of the wand could cause hundreds of particles to be spawned, our system needs to be able to create them very quickly. More importantly, we need to make sure that creating and destroying these particles doesn't cause memory fragmentation. The curse of fragmentation. Programming for a game console or mobile device is closer to embedded programming than conventional PC programming in many ways. Memory is scarce. Users expect games to be rock solid, and efficient compacting memory managers are rarely available. In this environment, memory fragmentation is deadly. Fragmentation means the free space in our heap is broken into smaller pieces of memory instead of one large open block. The total memory available may be large, but the largest contiguous region might be painfully small. Say we've got 14 bytes free, but it's fragmented into two 7-byte pieces with a chunk of in-use memory between them. If we try to allocate a 12-byte object, we'll fail. No more sparklies on the screen. It's like trying to parallel park on a busy street where the already parked cars are spread out a little bit too far. If they bunch up, there would be room, but the free space is fragmented into bits of open curb between half a dozen cars. Okay, so we start with the heap is initially empty. We allocate object foo, comes in here. Then we allocate bar, comes in here. Delete foo, leaving heap into two fragments. If we try to allocate another bar, it won't fit anywhere. Can't fit it there, can't fit it there. Here's how a heap becomes fragmented and how it can cause an allocation to fail, even where there's theoretically enough memory available. Even if fragmentation isn't frequent, it can still gradually reduce the heap to an unusable foam of open holes and filled in crevices, ultimately hosing the game completely. Most console makers require games to pass soak tests, where they leave the game running in demo mode for several days. If the game crashes, they don't allow it to ship. While soak tests sometimes fail because of a rarely occurring bug, it's usually creeping fragmentation or memory leakage that brings the game down. I mean, I can't even imagine trying to leave up my browser for several days. I don't think it would pass the soak test very well. Like, Firefox is getting better, but just most of them still have memory leaks of some kind. Nevertheless, talking about like the websites that they're on, like there's not much the browser can do about those memory leaks. The best of both worlds. Because of fragmentation and because allocation may be slow, games are very careful about when and how they manage memory. A simple solution is often best. Grab a big chunk of memory when the game starts, and don't free it until the game ends. But this is a pain for systems where we need to create and destroy things while the game is running. An object pool gives us the best of both worlds. To the memory manager, we're just allocating one big hunk of memory up front and not freeing it while the game is playing. To the users of the pool, we can freely allocate and deallocate objects to our heart's content. The pattern. Define a pool class that maintains a collection of reusable objects. Each object supports an in-use query to tell if it's currently alive. When the pool is initialized, it creates the entire collection of objects up front, usually in a single contiguous allocation, and initializes them all to the not in use state. When you want a new object, ask the pool for one. It finds an available object, initializes it to in use, and returns it. When the object is no longer needed, it is set back to the not in use state. This way, objects can be freely created and destroyed without needing to allocate memory or other resources. When to use it. This pattern is used widely in games for obvious things like game entities and visual effects, but it is also used for less visible data structures such as currently playing sounds. Use object pool when you need to frequently create and destroy objects. Objects are similar in size. Allocating objects on the heap is slow or could lead to memory fragmentation. Each object encapsulates a resource such as a database or network connection that is expensive to acquire and could be reused. Keep in mind, you normally rely on a garbage collector or new and delete to handle memory management for you. By using an object pool, you're saying, I know better how these bytes should be handled. That means the onus is on you to deal with this pattern's limitations. The pool may waste memory on unneeded objects. The size of an object pool needs to be tuned for the game's needs. When tuning, it's usually obvious when the pool is too small. There's nothing like a crash to get your attention. But also take care that the pool isn't too big. A smaller pool frees up memory that could be used for other fun stuff. Only a fixed number of objects can be active at any one time. In some ways, this is a good thing. Partitioning memory into separate pools for different types of objects ensures that, for example, a huge sequence of explosions won't cause your particle system to eat all of the available memory, preventing something more critical like a new enemy from being created. Nonetheless, this also means being prepared for the possibility that your attempt to reuse an object from the pool will fail because they are all in use. There are a few common strategies to handle this. We could prevent it outright. This is the most common fix. Tune the pool sizes so they never overflow regardless of what the user does. For pools of important objects like enemies or gameplay items, this is often the right answer. There may be no right way to handle the lack of a free slot to create the big boss when a player reaches the end of the level. So the smart thing to do is make sure it never happens. The downside is that this can force you to sit on a lot of memory for object slots that are needed only for a couple of rare edge cases. Because of this, a single-size pool may not be the best fit for all game states. For instance, some levels may feature effects prominently, while others focus on sound. In such cases, consider having pool sizes tuned differently for each scenario. Just don't create the object. This sounds harsh, but it makes sense for cases like our particle system. If all particles are in use, the screen is probably full of flashing graphics. The user won't notice if the next explosion isn't quite as impressive as the ones currently going off. We could also forcibly kill an existing object. Consider a pool for currently playing sounds, and assume you want to start a new sound but the pool is full. You do not want to simply ignore the new sound. The user will notice if their magical wand swishes dramatically sometimes and stays stubbornly silent other times. A better solution is to find the quietest sound already playing and replace that with our new sound. The new sound will mask the audible cutoff of the previous sound. In general, if the disappearance of an existing object would be less noticeable than the absence of a new one, this may be the right choice. Increase the size of the pool. If your game lets you be a little bit more flexible with memory, you may be able to increase the size of the pool at runtime or create a second overflow pool. If you do grab more memory in either of these ways, consider whether or not the pool should contract to its previous size when the additional capacity is no longer needed. Memory size for each object is fixed. Most pool implementations store the objects in an array of in-place objects. If all of your objects are the same type, this is fine. However, if you want to store objects of different types in a pool or instances of subclasses that may add fields, you need to ensure that each slot in the pool has enough memory for the largest possible object. Otherwise, An unexpectedly large object will stomp over the next one and trash memory. At the same time, when your objects vary in size, you waste memory. Each slot needs to be big enough to accommodate the largest object. If objects are rarely that big, you're throwing away memory every time you put a smaller one in that slot. It's like going through airport security and using a huge carry-on luggage tray just for your keys and wallet. When you find yourself burning a lot of memory this way, consider splitting the pool into separate pools for different sizes of object. Big trays for luggage, little trays for pocket stuff. This is a common pattern for implementing speed-efficient memory managers. The manager has a number of pools of different block sizes. When you ask it to allocate a block, it finds in an open slot in the pool of the appropriate size and allocates from that pool. Yeah, I hadn't really thought about like multiple pools to handle this type of thing. I always thought like it would just be a single array, and we just go through that. Reused objects aren't automatically cleared. Most memory managers have a debug feature that will clear freshly allocated or freed memory to some obvious magic value, like, whatever that is. This helps you find painful bugs caused by uninitialized variables or using memory after it's freed. Since our object pool isn't going through the memory manager anymore, when it reuses an object, we lose that safety net. Worse, the memory used for a new object previously held an object of the same exact type. This makes it nearly impossible to tell if you forgot to initialize something when you create a new object. The memory where the object is stored may already contain almost correct data from its past life. Because of this, pay special care that the code that initializes new objects in the pool fully initializes the object. It may even be worth spending a little bit of time adding a debug feature that clears the memory for an object slot when the object is reclaimed. Clear it to dead Bob. Unused objects will remain in memory. Object pools are less common in systems that support garbage collection because the memory manager will usually deal with fragmentation for you. But pools are still useful there to avoid the cost of allocation and deallocation, especially in mobile devices with slower CPUs and simpler garbage collectors. If you do use an object pool in concert with a garbage collector, beware of a potential conflict. Since the pool doesn't actually deallocate objects when they're no longer in use, they remain in memory. If they contain references to other objects, it will prevent the collector from reclaiming those too. To avoid this, when a pooled object is no longer in use, clear any references it has to other objects. Yeah, I can see that would be a little bit tricky. It signalized, good morning! Yes, we're doing a JavaScript today, and then most likely tomorrow we'll go through this exact chapter and do rest with it. But we'll see what it's like. All right, moving on to sample code. Real-world particle systems will often apply gravity, wind, friction, and other physical effects. Our much simpler sample will only move particles in a straight line for a certain number of frames and then kill the particle. Not exactly film caliber, but it should illustrate how to use an object pool. We'll start with the simplest possible implementation. First up is the little particle class. All right, so let's start implementing this in JavaScript. So class particle. And so we have a constructor here that we're going to store frames left. So this dot frames left equals, well, we don't know what we're going to initialize it to right this second, so I'll just set this to be 0. Then we have an init method, which takes in a x and a y, so I'm guessing this is the location, the x velocity, the y velocity, and the lifetime. And so this dot x equals, maybe we can set these to like null to begin with. That way if we get a null error, we know we didn't initialize it correctly. Okay, so we have x, we have y, so this dot y equals null. This dot velocity, this dot y velocity, and of course we have frames left already created. So then down here in init, we're going to do this dot x equals x, this dot y equals y, this dot x velocity equals x velocity, this dot y velocity equals y velocity, and this dot frames left equals lifetime. And then we're going to have a method named animate. Okay, so we're going to check to see if we're not in use. And we have this in use right here. So let's go ahead and do this. This would be like a getter potentially in JavaScript classes. So we can do an in use here. And we're going to return this dot frames left is greater than 0. So the way we can use this getter is if this dot in use, and I don't need the parentheses because it's a getter, so we can use it almost like it's a computed property. So if this is in use, then we want to do an early return. Now, if we get past that line, then we're going to this dot frames left minus equals to 1. So reduce the number of frames that this specific particle has left. Then we're going to do this dot x plus equals this dot x velocity, this dot y plus equals this dot y velocity. Okay, so then that's going to have it move around for us. And of course we have these like private things. The default constructor initializes the particle to not in use. A later call to init initializes the particle to a live state. Particles are animated over time using the unsurprisingly named animate function, which should be called once per frame. The pool needs to know which particles are available for reuse. It gets this from the particle's in-use function. This function takes advantage of the fact that particles have a limited lifetime and uses the frames left variable to discover which particles are in use without having to store a separate flag. The pool class is also simple. So now we have class particle pool. All right, so I don't see a constructor in here, but we probably want one. So we have a create method here, which I don't see it actually creating. Oh, they're gonna just like have it created here. So we're gonna have a create, which is gonna take an X and a Y, an X velocity, a Y velocity, and a lifetime. So this is really interesting. The pool doesn't care about where it's created. It's just going to like pass that through. So somebody else is going to call create off of particle pool to create the particle. Then we're going to have animate. So here we're going to loop through whatever the pool size is. That looks like it's going to be a constant. And we're going to set that to be 100. And I know this constant is inside of the class, but we don't really get that ability in JavaScript. Although what I could do is, instead of like a constant quite like this, we could have a constructor. And then we can just say this dot pool size equals 100. Just initialize it to that. We also have particles. So this dot particles equals, and we're going to create an array that's going to be of that like specific size. So new array of size, this dot pool size. And that's going to create us an array of 100. So like we get that array now. And so we're going to create later and then animate. So in animate, we're now going to loop through all of the particles and run animate on them. And so we could do this with like the for loop like that, or we can use an array method. So this dot particles dot for each. We'll get a particle, and then we're going to run particle dot animate. The create function lets external code create new particles. The game calls animate once per frame, which in turn animates each particle in the pool. This animate method is an example of the update method pattern. Right, so it's the equivalent of like being able to call update on it. The particles themselves are simply stored in a fixed size array in the class. In this example implementation, the pool size is hard-coded in a class declaration. But this could be defined externally by using a dynamic array of a given size or by using a value template parameter. Creating a new particle is straightforward. Okay, so here's where we're going to create the particle here. So find an available particle. So we have to loop through until we find a particle that's not in use. And I don't necessarily want to like loop through multiple times. So probably a for loop in this case is good because we can get that early return. And you can't early return or like stop on the array methods, which is a little bit unfortunate. So we're gonna for let index equals 0, index is less than this dot particles dot length. Actually, this could be, it could be the pool size, yeah. It doesn't really matter. The property is kind of like static on this, so it should be pretty simple. Like it's not going to add any more complexity to, or it's not going to make it slower by checking the length as opposed to the pool size. It doesn't have to do the calculation. It keeps it up to date behind the scenes. And then index plus equals to 1. All right, so that gives us there. If that particle is in use, so if it's not in use, so if not particles, it's going to be this dot particles of position index dot in use. Okay, so if you're, and again, remember, I don't need to put the parentheses on it because it's a getter. So if it's not in use, then we're going to initialize it and pass it in all the stuff that we've got here. So this is going to be this dot particles index dot init, and then we're going to pass in all the appropriate things. So the x, the y, the x velocity, the y velocity, and the lifetime. And then we want to return out of here. Because, hey, we initialize this particle. We don't want to initialize it twice. We just want to initialize it once. We iterate through the pool looking for the first available particle. When we find it, we initialize it, and we're done. Note that in this implementation, if there aren't any available particles, we simply don't create a new one. That's all there is to a simple particle system, aside from rendering the particles, of course. We can now create a pool and create some particles using it. The particles will automatically deactivate themselves when their lifetime has expired. This is good enough to ship a game, but keen eyes may have noticed that creating a new particle requires iterating through potentially the entire collection until we find an open slot. If the pool is very large and mostly full, then we can get slow. Let's see how we can improve that. Creating a particle is O(n) complexity, for those of you who remember our algorithms class. Yeah, because we're just going through once. That's it. Dato, who I don't know if he's been coming to the stream recently, but a while back he was talking about, he was trying to get 200,000 particles on the screen at one time, and he was using a GGEZ game engine, and it just wasn't able to handle that, which is a little bit sad, but it's also like that's a lot of particles to render onto the screen. And so you definitely want to like not loop through every single time in case it was like the last particle that was free. A free list. If we don't want to waste time finding free particles, the obvious answer is to not lose track of them. We could store a separate list of pointers to each unused particle. Then, when we need to create a particle, we remove the first pointer from the list and reuse the particle it points to. Unfortunately, this would require us to maintain an entirely separate array with as many pointers as there are objects in the pool. After all, when we first create the pool, all particles are unused, so the list would initially have a pointer to every object in the pool. It would be nice to fix our performance problems without sacrificing any memory. Conveniently, there is some memory already lying around that we can borrow, the data for the unused particles themselves. When a particle isn't in use, most of its state is irrelevant. Its position and velocity aren't being used. The only state it needs is the stuff required to tell if it's dead. In our example, that's the frame's left member. All those other bits can be reused. Here's a revised particle. Okay, so what are we doing now to it? We have public, we have a get next. Okay, so we're gonna be creating like a linked list almost. So get next in particle, return state next. So what's state? I see state here. And there's this union. State when it's in use. I don't know what union is in C++. There's a interesting, okay, so this is a struct inside a particle. So almost like a class inside of a class. So we don't really have structures, but we could have this be just a pure object, like an object literal. Double x and y, double x velocity, and live. State when it's available, particle next, okay. We moved all the member variables except for frames left into a live struct inside a state union. The struct holds the particle state when it's being animated. When a particle is unused, the other case of union, the next member is used. It holds a pointer to the next available particle after this one. Interesting, so how would we set that? Okay, so we have this set next. There we go, okay, so I didn't really read that. Let's do this. We're gonna have a get next, return state.next. So if we follow this here in our constructor, we're going to have this dot next equals null. We're going to have this be a get next that then just returns. And so then we have this be like a state. So this, it might be better to have like a this dot state equals, it's an object that then holds next. Pretty much, okay, so that's going to be null to begin with. So then in get next, we're going to return this dot state dot next. And then we have set next. So set next takes the next particle and we're going to then do this dot state dot next equals next particle. So then we have our frames left. That's still here. We have this weird union. So the state, when it's in use, this is where like our x velocity and y velocity live. Live. I thought that was inside the brackets to begin with, but it looks like this is some kind of, is it telling the struct that it's alive? Like, is that a C++ thing? It looks kind of like it would be. So would this be now part of state? Yeah, okay, so this is part of state, and then we have live inside of state. Oh, that's weird. Okay, so hold on. This would then make inside of state. We have this x and y. Okay, so we have x, which is null, y is null, x velocity is null, y velocity is null. Okay, so we have that here. And that's under another struct of live. So would I put this under like live here? So we have live and it's data. Sort of like a nested data structure here now. Then particle next, which is in the union. The union just saves memory space. There's no need to copy that structure. Okay, so I don't actually, Union saves memory space. Also, good morning, Utsby. So I don't need anything like this. I'm just gonna keep it all inside of state. It almost doesn't make sense to like do that. Like I could just, like that seems, like shouldn't I just be able to do next here? And I guess like maybe it makes more sense in JavaScript to do next here and not have to do anything else. Let's just do next. All right, so again, we moved all the member variables except for frames left into a live struct inside of a state union. This struct holds the particle's state when it's being animated. When the particle is unused, the other case of the union, the next member, is used. It holds a pointer to the next available particle after this one. Unions don't seem to be used that often these days, so the syntax may be unfamiliar to you. If you're on a game team, you probably got a memory guru, that beleaguered compatriot, whose job it is to come up with a solution when the game has inevitably blown its memory budget. Ask them about unions. They'll know all about them and other fun bit packing tricks. In a union, either the struct or the next pointer would be the one in the one memory allocation. In JS, you may as well just have both and just access one or the other. Yeah, that makes sense because, I'm not doing manual memory management. We have a garbage collector, and I can't really turn that off in JavaScript. I wonder if I can do that in what other languages we can do these tricks with. I haven't really had to play with memory packing stuff with any other languages before. Just mainly the closest thing in JavaScript is just to being careful when I release all of my objects. The garbage collector didn't, try to get rid of 10 gigabytes. Was it 10 gigabytes? It was at least. It was at least hundreds and hundreds of megabytes worth of stuff, all at the same time, which was causing our app to pause for a minute, which sucked. Maybe not a minute. That might be a slight exaggeration, but it certainly felt a long time. Okay. Maybe Rest has a similar concept as it's intended as a systems language. Yeah, that's absolutely true. When we get to this part, we might explore memory packing in this way. But yeah, that will be really interesting. We can use these pointers to build a linked list that chains together every unused particle in the pool. We have the list of available particles we need, but we didn't need to use any additional memory. Instead, we cannibalize the memory for the dead particles themselves to store the list. This clever technique is called a free list. For it to work, we need to make sure the pointers are initialized correctly and are maintained when particles are created and destroyed. And of course, we need to keep track of the list's head. Okay, so in particle pool, we need now the first available. So here, this dot first available. And I guess we could just say this as 0. Zero is always the first one available to begin with. When a pool is first created, all of the particles are available. So our free list should thread through the entire pool. The pool constructor sets that up. Okay, so in the first one is it's a pointer to the actual first particle. Okay, hold on. So this is going to be this dot particles of position 0. So it's not just an index of it. It's going to be the actual a reference to the particle. Then we're going to loop through, so each particle points to the next. So we need to loop through every particle and point it to the next particle, except the last one, of course. Oh, interesting. And the last one terminates the list. Okay, so yeah, we're gonna loop through it, except almost going to the last one, but not really. So here, let's do that. So we're gonna do for let index equals 0. Index is less than this dot particles dot length, but then we're gonna subtract by 1 also. Index plus equals to 1. So then in our for loop, we're going to set next to be the next particle. So we're going to do this dot particles of position index dot, I think I can do, so next, call it as the, as a variable here, or actually no, we don't have to do that. We need to set this equal, because it's a setter. in this set next. And then we need to set that to be the next particle. This dot particles of position index +1, like that. So that will make that happy. And then the last one terminates the list. So after this, we're going to do this dot particles of position, this dot particles dot length -1 dot next equals null. Okay, so set that to there. Now to create a new particle, we jump directly to the first available one. Ooh, okay. Now this is nice looking. Chantilly Cake, good morning. Hello, hello, hello. Okay, so in particle pool, we now have create here. It's gonna be the exact same thing. We take our XY velocities and lifetime. We make sure the pool isn't full. Okay, so assert that the first available isn't null. So we're gonna throw an error in the case that it is null. So this is if this dot first available is null, which means we can basically just say if first available, if not first available. Then we want to throw new error, and we just want to say no more, like this error is pool is full. We want to remove it from the available list. Okay, so particle, new particle equals first available. Okay. All right, I get it. So we're just, it's a linked list. Like it's a standard linked list type thing. We're going to extract out that new particle here. So we're going to say const new particle. We could even just do particle in this case. Equals this dot first particle, first available. And I think it's then just get, right? Oh, no, first available is a pointer to that first particle anyways. So we're fine with that. So we store this away. Then we want to update to whatever we have, like the next one is in here. So we update that pointer. So then we're gonna say this dot first available is now gonna be equal to particle dot next, like that. And this next is a getter, so we're gonna get the next one. Also, this isn't really this dot state anymore. We decided this dot next because we have next right there, which will be null in case it doesn't exist. This for loop, therefore, is no longer needed. And then, of course, we have to create the particle. So we're going to do particle dot init, then just pass everything through. So x, y, x velocity, y velocity, and then the lifetime. We need to know when a particle dies so we can add it back to the free list. So we'll change animate to return true if the previously live particle gave up the ghost in that frame. Okay, so now we have particle animate. So in animate here, we want to return a Boolean in case we're in use anymore. Now, I see like we can just do this calculation here. Oh, this is gonna be like an is dead. And I wonder if it would make sense to like actually create an is dead here and then use that as well. So if I do that, to get is dead, return this dot frames left is equal to 0. So if we do that, then here I want to return this dot is dead. When that happens, we simply thread it back onto the list. Okay, so we're gonna have particle pool animate for X. For int 0, pool size, all that stuff, particle pool. Line 34. What's your question? ZXZap, return this dot frames left is equal to 0. Or do you have a question? Equals. Well, I mean, it doesn't really matter. I could definitely do this. Like this works. And it also works with the other thing. I don't know, this is like my personal opinion. In JavaScript, I sort of feel that we went a little bit like too far into like, we must use like, check both type and value at the same time. Like we don't want it to coerce. However, in this case, I know it can never be a string because I'm setting it. Oh, you wanted to test the command? Yeah, it definitely works too. That's pretty awesome. You could also like add in a string when you do the line, and then I'll be able to see it when I hover over it. But yeah, I really love that line thing. All right, so continuing on. When this happens, we simply thread it back onto the list. So var particle animate. Okay, so now we get a check to see if we animated it. So for each particle, if particles animate. Okay, so this is now going to be like a little bit more complex than what we had here. So let's go ahead and wrap this in here. All right, so then we're going to wrap this in a Boolean. So if, or I guess an if statement. So if particle.animate, so if this works and we don't get false back, or if we do get false back, then we want to now remove it. So particles of index, which means we also need the index here. We then want to set the next to be the first available. So, right, okay, so if you're dead, if you died, particles of index set next to be the first available. So what is that going to be? That's going to be this dot particles of index. Now this is this exact one. So I could just do particle dot next is equal to this dot first available. And then we set first available to be equal to particles of index, which is this, like this particle. Oh, because it's dead, it's available now. Add this particle to the front of the list. Okay, so then we're going to do this dot first available and set this equal to the particle. So particle. So set this to the front of the list. Okay, I get it now. So we're going to be looping through all of the particles. And hey, you're dead. I don't need index here. It's like, you died. Okay, so you if you died as part of your animation, then immediately we want to store off the first, like what we have as the first available, and just say like, hey, what we have as the first available, you now point to that as your next. Also, first available becomes you. And then we move on to the next one, and it does the exact same thing over and over and over again. So it just sort of like constantly appends them all. So we have lots of particles falling off the screen and dying, then we, this will happen a lot, every single frame. Chantilly, you've been playing the drop game a lot. All right, but doesn't look like I missed anything. Okay, so moving on. There you go, a nice little object pool with constant time creation and deletion. Design decisions. As you've seen, the simplest object pool implementation is almost trivial. Create an array of objects and reinitialize them as needed. Production code is rarely that minimal. There are several ways to expand on that to make the pool more generic, safer to use, or easier to maintain. As you implement pools in your games, you'll need to answer these questions. Are objects coupled to the pool? The first questions you'll run into when writing an object pool is whether the objects themselves know they are in a pool. Most of the time they will, but you won't have that luxury when writing a generic pool class that can hold arbitrary objects. If objects are coupled to the pool, the implementation is simpler. You can simply put an in-use flag or function in your pooled objects and be done with it. Sort of like our in-use, like, you know, is it alive? You can ensure that the objects can only be created by the pool. In C++, a simple way to do this is to make the pool class a friend of the object class, and then make the object's constructor private. Okay, so in particle, we have friend class particle pool. Then private particle in use, pool in use, and then we have particle pool, which then like creates these. Oh, okay, I get it. So then like when we create the particle pool, we need to actually loop through and initialize a new particle for every single one, which we're not actually doing here. So this wouldn't work too well because we just have this array, or we're not like actually going through it. So to initialize this, we would want to do a for each, I guess, here. Not a for each because an array doesn't have anything in it right now. So we probably want, we could actually do a for each. Okay, let's do that. We'll do this dot particles dot for each. We're gonna get the particle, the index, and then the actual, like all the particles. And so then in here, we want to initialize a new particle into each position in the index. So we're gonna have particles of position index is equal to a new particle, like that. We're not using particles, so I'm gonna put an underscore in front of it to tell VS Code that we don't need to worry about that. And that creates a new particle. So we've now initialized our array. And in sort of like this friend class thing, we'd be saying, you know what, this constructor can only be called by particle pool. This relationship documents the intended way to use the class and ensures your users don't create objects that aren't tracked by the pool. You may be able to avoid storing an explicit in-use flag. Many objects already retain some state that can be used to tell whether it is alive or not. For example, a particle may be available for reuse if its current position is off screen. If the object class knows it may be used in a pool, it can provide an in-use method to query that state. This saves the pool from having to burn some extra memory, storing a bunch of in-use flags. If objects are not coupled to the pool, objects of any type can be pooled. This is the big advantage. By decoupling objects from the pool, you may be able to implement a generic reusable pool class. The in-use state must be tracked outside the objects. The simplest way to do this is by creating a separate bit field. Okay, so we have, a template now. I'm not familiar with templates. So we have a generic pool. We have the size of the generic pool. Obviously, like the pool itself, which is created as an array of pool size, and then a separate array that holds in-use booleans. So index it. So we can say like, hey, index of 1, are you in use? What is responsible for initializing the reused objects? In order to reuse an existing object, it must be reinitialized with new state. A key question here is whether to reinitialize the object inside the pool class or outside. If the pool reinitializes internally, the pool can completely encapsulate its objects. Depending on the other capabilities your objects need, you may be able to keep them completely internal to the pool. This makes sure that other code doesn't maintain references to objects that could be unexpectedly reused. The pool is tied to how objects are initialized. A pooled object may offer multiple functions that initialize it. If the pool manages initialization, its interface needs to support all of those and forward them to the object. Okay, so we have class particle. We have multiple ways to initialize. Yeah, we don't have this type of overloading. Is that what it's called? Method overloading? Where we basically say, hey, like we have init, and depending upon what you pass in, just call which one of these. Yeah, we don't have that in JavaScript. Then we have our particle pool, which then is going to also have like create based upon what we pass into it, which then forwards on and inits. Oh yeah, you did create a little tree. That's pretty cool. If outside code initializes the object, the pool's interface can be simpler. Instead of offering multiple functions to cover each way an object can be initialized, the pool can simply return a reference to the new object. Okay, so we have the class particle. I mean, we still have these like multiple ways of initting it, which we can't do in JavaScript. We have this particle pool. When we do create, we pass in return a reference to the available particle, which then gets like initialized outside. The caller can then initialize the object by calling any method the object exposes. So basically, yeah, pool.create, call this, and then we can do like dot, arrow, whatever. So like then dot, because we have an instance to the object, and then pass in what we want to do. Outside code may need to handle the failure to create a new object. The previous example assumes that create will always successfully return a pointer to an object. If the pool is full though, it may return null instead. To be safe, you'll need to check for that before you try to initialize the object. Okay, so we have particle, pool.create. If particle is not equal null, then, okay, yeah, so we need to do that. Now handle null, essentially. See also. This looks a lot like the flyweight pattern. Both maintain a collection of reusable objects. The difference is what reuse means. Flyweight objects are reused by sharing the same instance between multiple owners simultaneously. The flyweight pattern avoids duplicate memory usage by using the same object in multiple contexts. The objects in the pool get reused too, but only over time. Reuse in the context of an object pool means reclaiming the memory for an object after the original owner is done with it. With an object pool, there isn't any expectation that an object will be shared within its lifetime. Packing a bunch of objects of the same type together in memory helps keep your CPU cache full as the game iterates over those objects. The data locality pattern is all about that. So then that's where we get, yeah, like everything is like closer together. It runs through it. The CPU, the CPU is not our bottleneck here. It's like the memory access in that case. But I think like I do like this pattern in general. We're able to create like the object pool. I don't know for JavaScript, having the sort of like next in here is probably fine. There's no like sort of, I'm not aware of those like memory tricks, sort of like what Oopsby was saying, which is, hey, look, we can do the next thing. Like have next instead of like these other things here. So I think this will be good. As Oopsby was saying, I don't know if we're gonna have like any clever things we can do with Rust that would allow us to do that sort of like the memory packing, as it were. But this is like pretty interesting in our own sort of like setting for it. So I like it. And so with this, we're done with this this chapter. So I'm gonna go ahead and put